So it is if UV belongs to relation R, then comes from A and V comes from B. Naturally, since a relation is a subset of the Cartesian product, the number of the set of possible relations between A and B is the power set of the Cartesian product, which is written as 2 to the power A cross B. Now, very specifically, oftentimes A and B could be the same set. So we say that R is a relation over the set A. So in such cases, there are several properties that we are aware of. One is its relation is said to be reflexive if for every element in A, every element T in A, TT belongs to R. So if every element is related to itself. It is symmetric if the order is immaterial. That is, if UV belongs to the relation, VU also belongs to the relation. It is transitive if UV and VW, if U is related to V and V is related to W, that means that U is related to W. Then we'll say it is transitive. It could be antisymmetric, which means that if UV and VU both belong to R, the relation, then U and V are necessarily the same element. And we say that if a relation is reflexive, symmetric, and transitive, then it's an equivalence relation. And you know that equivalence relations typically represent partitions of the set. For example, if you take natural numbers and say any natural number n, say 7, and you try to define a relation in terms of the modulus of by 7. So if you divide a number by 7, then what is the remainder that you get? And if you put these, consider this relation, then that is an equivalence relation. That is, any two elements which have the same remainder when divided by 7 is considered to be in the same set, and that induces a partition of based on the remainder. So it's a equivalence relation that you will have. You all know all this, just quickly doing a recap. A relation may be over of arity n over n sets a1 to an, and it could be actually decomposed into a number of binary relations. Now, the specific type of relations which we will use more frequently are called functions, which again you know, f is a function from a to b. If it is a relation over AB, which means f is necessarily a set of doublets coming from the Cartesian product of the set A and B. But it has a constraint that if I have two doublets S1, S2 and T1, T2, where the first component is same, that is S1 is equal to T1, then S2 must be equal to T2, which means that one element cannot map to two different elements. One element of A cannot map to two different elements of B, which is possible in a relation, but it is not possible in a function. Now, we say that we take functions as total, which means that for every element in A, there is a mapping that exists in F. So if that happens, then we say it is a total function. Otherwise, it is a partial function. So there are some elements. So more often, we will deal with functions which are total, but in some cases, it could be partial functions as well. If you consider the constraint on the function, then you will see that the number of functions that you can have from A to B is the size of B, or the number of elements in B raised to the power of the number of elements in A. So that is what happens. So the set of functions from A to B is represented as B to the power A. This, and naturally it is a subset of the power set of A cross B, the Cartesian product of AB. A is called the domain, B is called the codomain or range. We say that if A is the image of F, that is It is the collection of all elements to which at least one element of F maps to. Now, based on this notion of image, we can characterize the total functions as either injective. An injective function means that no two elements of A map to the same element in B. They always map to. So if they map to the same element, then in the domain, they must be same as well. So it basically means that no two elements map to the same element in B. It is an injective function. A function is, it's also called one-to-one. A function is surjective if the image of F is same as B, which means that every element in B has been mapped to at least from one element in F. And a total function that is onto as well as one-to-one is called bijective, which is injective as well as surjective. So some functions are bijective, and we'll say F inverse of F is the collection of doublets where the order is just reverse. So it is inverse mapping from B to A. Naturally, if a function is injective, only then F inverse can be a function, because otherwise there will be two elements of A mapping to the same element in B. So when you change the order of the doublets, then the element in B, that particular element in B has two different mappings in the set A, which violates the requirement of a function. So if it is a function, inverse can exist if it is injective, otherwise it will not exist. Similarly, if a function is surjective, then every element in B will have a mapping onto A, because it has been mapped onto. So if a function is surjective, only then F inverse can be actually a total function. Otherwise it will be a partial function. So in general, we can say F inverse is a function if and only if F is a bijection. Otherwise, it will be a relation. So this is a basic fundamental about functions which you knew. I just flipped through. Then we have function composition. That is, if we have two functions F and G, I'm just taking examples to illustrate, make it easier. Then F composition G is another function where you first apply G, and then on the result of G you apply F. So F composition G of X is Gx being used as a value, as a parameter for F. So if you compute Gx here, F composition Gx here, then you have F of Gx, which is Gx is x plus 1. So it's a F of x plus 1, which is necessarily x squared plus 2x plus 1. If you change the order in the composition, if you do G composition F, that is, if you apply F first and then G, then you have G of F of x. F of x is x squared. So if you apply G on that, you get x squared plus 1. So you can very easily see with this simple example that the order does not preserve the function in composition, or in other words, function composition is not a commutative operator. Now, our next question is, what is this composition? The composition itself is a function. So start thinking about this now. This is getting into a little bit of where we want to be. That is, so far, primarily you have talked about functions which take values which are just like number sets like that. So fx is x square is a function, so x is a number. Gx is x plus 1, x is a number. But what is this composition function, the one that is represented by this round here? It takes two different functions f and g and gives you a new function. So this notion is what you will have to slowly get very used to, that the parameter of a function could be another function itself. Similarly, the result of a function could be a function itself. So these are what called typically as a higher order function, and lambda will be full of such higher order functions. So if I have a function from z to z, f and g, because I'm doing it both ways, so it has to be for the same domain and codomain. So if f is from z to z and g is from z to z, it takes two different parameters. So it takes a pair of f and g. So what the composition takes as is a doublet fg. So naturally it is an element of the cross product of all functions from z to z with all functions of z to z, and that doublet maps to a function which is from z to z. So as we see that when f comes from the first component, g comes from the second component, f composition g, the result of the composition is actually doing x plus 1 whole square. Right. So this is the new function which takes x and give you x plus 1 whole square. Similarly, this composition function, this composition where g comes from the first element and f comes from the second, gives you another function of x, which is x squared plus 1. So this is, I'm repeating again, that this is a critical notion that functions could be parameters themselves and could come as a result. So it is not necessary that we will only have non-function values as parameters or results, right? So this is the function composition that we'll frequently use. Next, I introduce a very simple notational concept called currying or current function. The name currying came from Haskell Curry. So Haskell, the name Haskell you are familiar with in terms of the language. Yes, he was a mathematician. So Haskell Curry used this mechanism to study functions. Now there is the interesting story that actually Moses Schonfinkel developed currying before Curry did, but it did not get recognized because he did not manage to show a lot of applications. So people just for a long time didn't know that Moses had actually done this well before Haskell did. So this simple mechanism is known as currying, where we use one variable functions only. So what currying is? Currying is a process by which you take a function of multiple variables and represent them in terms of one variable. So what do? It's something very simple. If h is a function of two variables x and y, let's say h is x plus y, then naturally the type of x is z cross z, because it is taking two parameters and gives you a result in z. That is in terms of integers. Z is integer. I didn't mention that, but that's a notational convention. Now from h we derive a current function hc, where it is a current function. What it does is it takes a value x, a fixed value of x. So if you put a constant value in x, what you'll get? You'll get a function in y only. So for example, say if you put x as 2, then you will get a function which is 2 plus y, which by itself is a function, but this function is of one variable only. So we can say that the current function h is a function which takes one value z. This form is the easiest to understand. It takes one value z in z, which is, we are here using it as 2, and gives me a function back. That function is h. That function is g. What is that function? That function is 2 plus y. So I can actually represent a function of two variable xy as a in terms of one variable function which are current. So that is the most uh, important observation to make here, because we are going to use this all through to ensure that we do not need to bother about number of variables in a function, because we can always, if there are three variables, we can first do a currying to get it to two variables, then do a currying to get it to a one variable function. So one variable functions are enough to represent everything, right? So two key factors that we have learned so far is one is of composition, the getting accustomed to the notion that functions can be parameters and functions can be result, and the concept of currying, that I can do a little bit of algebraic manipulation to represent a multi-variable function in terms of only one variable function. So these are the two key points which probably you did not know from your study of set algebra earlier. So let me stop at this point before I actually get into lambda calculus and see if there are any questions. If you have any question, please write it in the chat box, or unmute yourself and ask the question. This is simple, I understand, but this is very foundational and very fundamental in terms of understanding the whole concept of lambda calculus and its use. Okay, there is no question till now. So let me get back to the presentation. I've shared it again. So let me now introduce the concept of lambda. So lambda calculus was developed by Alonzo Charch and his doctoral student Stephen Cole Kleene. Kleene's name you have already come across possibly in terms of Kleene closure. If when you have done kind of flat and all that automata theory, you have come across uh, kind of Kleene closure in expressions and so on. This was done in the 1930s. And this calculus can represent all computable functions. You know that all functions, everything cannot be computed, because there are problems which are undecidable, which you cannot compute. But Turing machine can compute all functions that can be computed, or in other words, we put that whatever Turing machine can compute is a computable function, whatever you look at. So lambda calculus has that similar kind of power. So it is equivalent to a Turing machine. So any lambda calculus expression potentially can be used to create a Turing machine. Any Turing machine instance can be represented by a lambda calculus. So that's foundational more. We are not going to get into that level of theory because we are really interested in the application of lambda calculus. Here I have given a pointer to a lambda calculus overview source. If you need more material than what is there in the presentation, you can refer to this. Okay. So having said that, the lambda calculus is important because it has a uncomplicated syntax and semantics and provides a excellent vehicle for studying the meaning of programming languages. So all functional programming languages can be viewed just as syntactic variant of lambda calculus, and we'll see how denotational semantics can be used for programming languages which are from other paradigms as well. And we will repeatedly use the higher order functions of lambda calculus. Now coming to the concept of lambda, it is something very simple. It is a function which does not have a name. I mean, I just look at it in this way. So suppose you have a function cube which takes an integer and gives you an integer. It does a cube of that. Multiplied is 3 times. So cube n is defined as n cube. Now, question is, and understand carefully, can you tell what is the value of the identifier cube? Now, we do not associate anything with cube. What we know is what is the value when cube is applied on n, which is n cube. Cube is applied on 2, it is 8. Cube is applied on 3, it is 27. But what is cube? Does it really matter other than, other than human convenience to call this function cube? Instead of that, I could have called it tiger. I could have called it a table. I could have called it a box. But as long as given n, it gives me n cube, it remains the same function. So the cube is the computation of the function. That is a fact that it is n times n times n. This is the object which is associated with the notion of cube, with the notion of this function. So the question is, since I could, leaving normal convenience, I could call cube by any name. So obviously, I can ask that what if I do not give it a name? Then the name really doesn't matter. What matters is the object that name associates with, which is the computation that you do. So that brings us to the domain of what are called anonymous functions, or the basic of lambda notation, which is we write lambda n. Note this very carefully. This is all new. Lambda n, which means that n is a parameter, dot n cube. This is the function body. So you can simply think of this as a C function which takes a parameter n, and in its body you say return n multiplied n multiplied n. Right? That defines the function that maps each n in the domain to n cube. So this expression lambda n dot n cube, dot is used just to designate where the parameter ends and where the function body actually starts, is a value that is bound to the earlier identifier cube. Okay. So when we do cube 2, what we say that we are passing the value 2 to the parameter n, right? The actual parameter is 2. We are passing it for the formal parameter n, so that the every instance of n in the body of the function is replaced by 2 to evaluate it. N becomes 2. We simply say n becomes 2. Now we are not getting into those complications of parameter passing mechanism, whether it is called by value, it's called by reference, or it's called by name. Don't think about all of that. Just think that n takes the value 2. Right? So that is what we say is an application of a function. So cube is being applied onto 2 to get the result 8. We have been more comfortable calling this in the programming languages domain as invocation of function, calling the function. In this lambda calculus paradigm, we say it's an application of a function onto the parameter. So in lambda syntax, you write this application in this notation. So lambda n dot n cube is a function. The first part is a function. Then what you write is you are applying this function lambda n dot n cube onto 2. This first part is a function, second is a parameter. So you're applying it onto 2. That is, you are invoking the function call. Think about that. Which means you replace 2 for n in the body of the function. So you replace 2 for n in the body of the function, it becomes 2 cube, and the result is 8. Right. So this is how a function abstraction and a function application is conceived in lambda notation. A function abstraction is the definition of the function. Right? We know that in C, in Java, in any programming language, you will write function name, parameters, and then you will write the function body. Only then you can use that function. And we call that as a function definition. And in these programming languages which are not using Lambda, having a name is important, because by that name you apply the function, invoke the function for a specific value. But here we have the abstraction, which is the function definition, and we directly apply it to the parameters. So the function, what is the function? What is the value that cube is bound to? Is this whole expression. So we take that whole expression, function abstraction, apply it, invoke it for the parameter 2. So here is the abstraction and here is the application. So this is the basic concept of Lambda. It is as simple as that. Okay, now let's look into a little bit of issues that we'll get into. Suppose a function has 2 parameters. Right. So say n square plus m. So naturally for application it will require 2 values, say they are 3 and 4. Now the question is, how do you do this replacement? Would you replace 3 for n and 4 for m? If you do that, you get 13. Or you would replace 3 for m and 4 for n, you get 19. Right? So that order is important, right? And think about in programming languages, we often say that like languages like C dictate that the order of the parameters have to be same between the call and the definition of the function, even when you are using default parameters. That's the reason that default parameters has to come at the end to the right. But the order of the parameters, actual parameters, and the order of the formal parameters are taken to be the same, so that you can just take them as 2 lists which coincide in the order and you associate parameters in that form. Some programming languages have calling mechanism by name, where you can say that this parameter has this value, this parameter has this. So you're explicitly saying that the parameters have certain value. Those kind of notational complication does not exist for Lambda calculus. So in Lambda calculus, what you do is simply say that what we'll have to say in the abstraction, we have to say 2 things now. One is certainly the fact that it has 2 variables, n and m. So lambda n dot lambda m dot. So it says that there are 2 variables, and then the function body. So this is the abstraction. Now if we apply 3, 4 on it, what is important is that order of these lambda parameters or the binding is critical. If I apply this function on the doublet 3, 4, then 3 is to be associated with the first bound variable n, and 4 is to be associated with the second bound variable m. So this order is important. So what we saw in terms of the first application will be the result. The 13 will be the result. Just recall, I'll go back one slide. This 13 result will come if n gets 3 and m gets 4. So if my abstraction is this, then its application on 3, 4 is 13. But if I change the order of the variables m and n, so again, in terms of C, what you're doing, you are just changing the order in which you have written the parameters. Similarly, lambda m and lambda n, we have just changed that order with the function body remaining the same. Now, if I apply with 3, 4, I'll get the result 19. So what it goes on to say is the order of the parameters are important for a lambda expression, and they will be applied whenever I apply this abstraction on another lambda, then that will happen in the same order in which the lambda binding has been done in the abstraction. So if you look into real functional programming languages, most languages allow anonymous functions as values. For example, in scheme language, you can write this same thing in terms of this expression. Scheme explicitly uses the word lambda to represent the this notation lambda. Or standard ML does that in terms of fn. He said f of n is this. So I mean, these are different language specific notations, and interestingly now C++11 has onwards has lambdas included. So we will talk about C++ lambda syntax and applications in a different module. So these are basic concept of lambda. So now let me again stop before I get into the actual expression and see if there is any question. It's a cozy winter morning, so I'm not sure if everybody is listening or just dozing off, you know. Anyway, that doesn't seem to be a question, so I'll continue. Please stop me in the middle if you have a question in the middle also. Just turn on your mic and ask me the question. So I'm back to the presentation, and let me now take a look specifically at the syntax of lambda expression. Lambda expressions come in 4 varieties, and this is something which is again interesting. Is in normal function programming languages, we differentiate between this is a function and this is a value. This is a value that I can send as parameter, this is a value that I can get as result, and this is a function. In lambda, everything is a lambda expression. A value itself is a lambda expression, the function itself is a lambda expression. A lambda expression can be applied on another lambda expression to get a lambda expression. So everything is in terms of lambda. So what you have are first type that you can have are variables, and we'll usually use lowercase letters to represent variables. So any variable is a lambda expression. We will have some predefined constants which can act as value or operation. As you can understand that in the domain of lambda, there is no differentiation between a value and a function. So predefined constants could be values or they could be operations. Actually, strictly speaking, if you talk about pure lambda calculus, predefined constants are not there. Everything you'll have to build up from scratch. But it gets very complicated to do that, very verbose to do that. So what we allow in what is called applied lambda calculus or impure lambda calculus is we allow a few values and operations as predefined. So we take them as constant lambda expressions. And then we have just the 2 things I talked about. We have function applications, that is applying one function lambda expression onto another, which is invoking the function. And we have lambda abstractions, which are function definitions, right? So these are the 4 things that we have. So if I write it in the Backus-Naur syntax that you are familiar with for programming languages, then a lambda expression is either a variable represented typically by lowercase letters, or a constant, which is a predefined object, or it is a combination, or in other words, application, where you have 2 expressions within this parenthesis. So this first expression is being applied on the second expression. Cube is being applied onto 2. That's the basic thing. And then you have abstraction, which is also written in this manner: lambda followed by variable. You have already seen this example, lambda n dot n cube, n into n into n, right? So this is the expression. So you have In short, a expression is a variable, which is either a variable or a constant, or an expression applied onto an expression, or lambda v, you are binding a variable, treating it as a parameter, and applying it onto a lambda expression E. These are the only possibilities of lambda expressions. Pretty simple and compact. Okay, so what could be the constants? For example, there could be just value constants like numerals. More often we will talk about integers only here, and even more often we will talk about just natural numbers. But anything else is possible. So we assume that numerals are predefined constants. For example, the numeral 34, numeral 22. And we will assume that there are some predefined functions which are already known, for which you do not have to. So these are kind of the primitives of lambda expression, like add, mul, successor, square. So these are there. So you already know what is the expression for them. So these are the predefined constants that. So just to dig into a different domain and associate with a very old language, as I talked about yesterday, is kind of contemporary of Fortran only, is Lisp. So Lisp has these operations. One is a head or car. It's typically called car. One is a which returns, if I'm given, Lisp is all about lists and lists of elements, where elements could be anything. So and there could be another list also. So if I'm given a list, then head or car returns the first item of that list, head of the list. Tail, or this is typically CDR, since you cannot pronunciate it easily, you call it kudur. So tail or kudur returns a new list consisting of all but the first item. So understand, head is just an element, the first element, and tail is a list. It is not an element. It's a list excluding the first element. Then cons is what takes an element and a list and puts that element in the head of the list. So it actually goes on to construct a list. IsEmpty is a Boolean checker which returns true if there is no element in the list or the list is nil. Nil is another defined constant, which means that it's a null list. Otherwise, isEmpty will return false. So here are examples of Lisp expressions. A cons y nil. So cons has to take an element and a list and construct a list. So this is a null list. It has nothing. It takes element y and puts at the head. So I get a list containing y. Now if I do cons x y, list containing y, this is the list containing y, then I get a new list where x is in the front. So a list containing x, y in that order. Now if I do cons xy, cons puts x ahead of the list being formed from xy. So car will necessarily return x, the first element. Similarly, kudur will return the list on which this has been put. So these are kind of the relating axioms that define the interrelated semantics between these operations. When we talk about axiomatic semantics, you'll see that we'll talk more about this, but these are the basic facts which has to happen. So these are the things that you can, and you can certainly visualize that these are nothing but different notations for equivalent lambda expressions. Okay, now we introduce the concept of free and bound variable. It's a very simple concept. So if you have written an abstraction lambda v dot e, then v is said to be bound in E. Lambda v dot e makes v bound in the expression E. Think Equivalently, in terms of your C paradigm, so V is a parameter. So that parameter is bound in the function body. Now, all occurrences of other variables are free. For example, in a C function, besides the parameters, I could use a global variable, a variable which is not a parameter, which is coming from outside the scope of that function. Right? So that variable will be called free. The reason is simple. When I invoke the function, think about C itself, and that translates to lambda expression. When I invoke a function with given the parameters, if there are occurrences of free variables, or if there are occurrences of global variables in the function body, then the value of that function based on the value of the variable could vary, because it is dependent on something outside of the function, outside of parameters, which are global variables. So that is the reason these variables are called free. They can freely change the semantics of a function, the value computation of a function. Whereas a parameter is necessarily bound, because once you apply the function, it gets a value, and for that value only the computation has to happen, right? So that is the basic notion of bound variables, and we will very frequently use this free and bound variable in terms of using the lambda expression. So lambda v dot e means v is bound in e. So here is one example, lambda x, lambda y, and then it is xy. So this is the function. This part is a function abstraction. So x is bound in xy, y is bound in xy. But then you take this whole thing, abstraction, and apply it to yw, another lambda expression yw. Now this y is certainly free. So there's a little bit of tricky thing here, is the fact that in terms of name, both are called y. This is y, this is y, but this y is bound in xy. This y is free. So it could be anything. So we'll see. This will create confusion, obviously, when we try to interpret lambda expressions, and we'll see different, while we deal with semantics, we will see certain rules to rename free variables if required, so that we can actually do not get into this kind of a difficulty. Okay. So function application, so if you, it's written as this notation, as we say. So E1 applies to E2. So if E1 is like this, lambda x dot E3, then all free occurrence of x in E3, you replace x by E2. Right? Now, mind you, x is bound in this lambda expression. In E3, it has to be free. If you just look at E3 separately, because unless it is free, you cannot change its value. There could be other variables in E3 which are bound. Right? So just to give you an example, so this is E1, lambda n dot n cube is E1, and E2 is 2. So you're applying this function on 2. So here lambda x is n, E3 is n cube. So in n cube, just n cube, the E3 part, just in n cube, n is free. So by this lambda binding of n, when you apply it onto 2, you replace this n, this free n, in E3 by 2, and you get 2 cube. You can, n cube is just a notational convenience, but we should actually write it in this way, where 2 is a predefined constant in lambda expression, N is a variable lambda expression. Star is a binary multiplication, which is another predefined constant. So what we are doing here is to define Q. We can say star NN. So star takes two parameters and gives you a value. So this actually is another function, which is the squaring function. So then you do multiplication again with the result of the square and n. So you get a cubing function. And then you replace 2 in this function body, in this expression E3. I'm sorry, E3 as in here, because in this expression n is free. You replace it by 2 and you get 8. Okay? So in such a combination or application of E1 onto E2, the function or the operator E1 is called rater, taking from the end of the word operator, and its argument E2 is called the rand. So, or the from the last of the word operand. So rater applies onto rand. We will, these are just, you know, kind of names that people use in this domain. So this is about the function application, and we'll use uppercase letters and identifiers beginning with capital letters as meta variables for lambda expressions. We'll talk more about that. Now, it is important to also note that function application associates to the left. So what is the meaning of E1, E2, E3? If I have three lambda expressions, one after the other, it means that E1 is first applied to E2. It is associating to left. So E1 is first applied to E2, and the resulting lambda expression is applied to E3. So you can easily see that in, I'm going back to slides. In this combination, E1 applies to E2. Obviously, this makes sense if E1 is a function abstraction, is a lambda abstraction, it's a function definition, right? E2 could be anything based on what is a possible parameter for E3 here. Could be. But E1 has to be an abstraction. So if I write an application notation within bracket 2, 3, then that does not have a meaning. It's an expression, right? But does not have a meaning because 2 cannot be applied onto 3, right? It has to be an abstraction. Only then it has a meaning. So a lot of lambda expressions could be nonsense. So here, when I do E1, E2, E3, I'm applying E1 to E2. So that is the left association. And you can see that that has to again give me an abstraction, because unless it gives me an abstraction, I cannot apply it to E3. Right? So it is, I'm applying function E1 onto lambda expression E2. I get another function, which is the result of this application, which I eventually apply to E3. So also what the association means is, if I wanted to apply E1 on the result of applying E2 onto E3, then I would require a parenthesis here. But if I just write without parenthesis, this is what it means. Okay? So the scope of the scope of a variable, bound variable in the abstraction, extends to the far right as possible. So if I write lambda x dot E1 E2 E3, it means lambda x as if there is a parenthesis here. So this whole thing is taken as a body. And x is a parameter to that function body. And it does not mean that you take, say, the first part, lambda x dot E1 E2, where E1 E2 is the body on which x is bound, and that abstraction is applied onto E3. And these two are meaning two different things, you can see. Just the placement of the parenthesis changes the meaning. This whole thing is an abstraction. Here, there's an abstraction and then there is an application. Right. So we say that between, and I would think of it in a different way also. I can think of this lambda x dot e1 as an abstraction, e2 applied onto e3 as lambda application, function invocation, and then an application of this lambda x dot e1 onto the result of e2 applied on e3. Right? I could have thought of that. In that case, I'll need a parenthesis here, then I'll need another parenthesis here. So if I simply write this, it means this without the parenthesis. So in other words, what we are saying is application has higher precedence than abstraction. These are possible applications, and this is abstraction. So if when we do this, we are increasing the precedence of abstraction over application. First we have abstracted, then we have applied. Whereas here, we do the applications, E1 applied onto E2, the whole thing applied onto E3, and then that makes the function body and we abstract. So that is the precedence rule which is used in the lambda calculus. So we have seen the associativity of application, which is left associative, and we have seen that between the two operations that can be done in the lambda domain, application has higher precedence than abstraction. So if I wanted to mean this, then I have to necessarily write it with a parenthesis, where E3 is not the abstraction lambda x dot e1 e2. This function is applied onto E3. Right? So this is a simple thing, and my candid advice to you all is, what I find convenient is whenever dealing with a lambda expression, even though it's a little bit bothersome, but whenever dealing with a lambda expression, I try to fully parenthesize it so that I don't make mistakes. Otherwise, if you just keep it free without parentheses, then it's quite possible that at some stage either you misinterpret the left associativity of function application, or you mix up in terms of the application and abstraction. Right? Now, another notational point is an abstraction allows a list of variables that abbreviates a series of lambda abstraction. So if I had this, that is an abstraction for E, which has 3 parameters, x, y, and z. So I could write it with full parenthesis like this. I can simply write lambda xyz. It simply means that lambda x dot lambda y dot lambda z. That's it. Right? So that's it, just for notational shortcut. Now, as we have said, that lambda expressions are basically lambda expressions. I mean, they are possibly unnamed function or variable or predefined constant, but they do not have a name. So which means that every time I have to deal with an expression, I have to write that whole expression out. Quite understandably, as the expressions keep on building up, this gets quite messy in terms of at least human understanding. In the machine, it's okay, because just a pointer will say that this is a lambda expression. So what we allow is we allow some names, meta names, I can say, to represent expressions. So this is just outside of lambda calculus. This is not same as calling the cube function as cube. This is all that we are saying, that I can say define cube is equal to lambda n dot n cube, where I'm just saying that this whole expression, wherever I talk of cube, it actually means this expression, nothing else. No application, no abstraction, nothing. It just means that. So it's a define and a identifier is just a way to give a unique name to an expression so that whenever I use that name, I mean that expression, right? Just for another notation. Example. So I say, first look at this on the lambda expression side. Lambda f, lambda x, and what is the body? This is application, right? F applied onto x. So I'm invoking f with the value x. I'll get a result. And then f application on that result. So what I'm doing, I'm basically taking x and applying f on it twice. So therefore, I call it by a name twice. So now if I write twice, I actually mean this expression, this whole expression. And then I'm applying twice onto, it needs f and x, two parameters. So this first part, lambda n dot add n1, starting from this parenthesis to this parenthesis, is the actual parameter value that I want to pass for f, right? Because that has to be the, we know the order is important. So this is f. And then I have 5, which will be taken as x. Right? Now, if you dig little deeper into what is this f, we see that it is an abstraction which says lambda n, whose body is add n1. Of this, add is a predefined constant which adds two numbers. One is a predefined numeral. So this will give me actually n plus 1 in terms of our understanding of computation. And this whole thing becomes a function which I'm putting as the value of the bound variable f in the lambda expression twice. And 5 is the value I put for the bound variable x in the lambda expression twice. So what will this do is it will first apply this on 5 fx. So I'll get 6. Then it will again apply this on the result 6. So I'll get 7. That's the way to use definitions. Now, as I said that often fully parenthesizing expressions may be convenient, but well, it might mean that parenthesis matching, unless you are using an editor which is built in with parenthesis matching markers, you might find that this gets a little messy. So here is an expression, a lambda expression. So if you look into the lambda abstraction in this, so I have lambda x dot this f n x. So this is the first abstraction. Then I have another abstraction on top of this, which is with lambda f. Then I have another which is in lambda n. So these are the different abstractions. So as abstractions proceed, I'm making the meaning clear by putting, so nothing is done for this except taking this whole thing within parentheses as an expression, using it here and putting a parenthesis to make that this is a separate lambda expression, using that here, putting parenthesis again. Similar thing you do here, lambda y gy is the first abstraction. Then you have another abstraction on top of this. So these are fully parenthesized components of the lambda expression. So now if you replace all of this here is what you get, which is fully parenthesized lambda expression. This is a fully parenthesized lambda expression. So this expression basically means this. So now even if you forget the rule of precedence or associativity of these, there can be no further mistake. But of course, the second other possibility of mistake creeps in as you get 5 closing parentheses here. And if you have a problem with the matching, you are into deep trouble. Okay, so that was about the lambda expression syntax and notation and what does it mean. I'll stop for a while to see if there is any question before I get into taking different, very typically used lambda expressions. So let me get back and see if there is a question. Uh, please explain the example on slide 21 again. Slide 21 again. Oh, this example. So here what we are saying is we are talking about free and bound. So this is abstraction. And then you have the application on this. So in terms of, if you take just this expression xy, x and y are both free. Now then you have done a lambda y dot on this. So lambda y dot xy, thus y gets bound. Then on that you have done another abstraction lambda x. So in lambda x dot lambda y dot xy, x and y both are bound. And then you are applying this whole thing on yw. Now this y is coming as a, so it is as if, I mean, if I think of C equivalent, it is as if you have defined a C function with parameters x and y as formal parameters, and you are calling them with actual parameters y and w. Now both are y, but they are different y, right? One is a formal parameter y, another is a actual parameter y. So they are, just by the syntactic name, they are not semantically equivalent. But in YW, but in this whole expression, there is no binding. There is no lambda on Y for this part, because this is, it goes up to the end. So this is where the
So,
parenthesis end. Yes.
but we have said that application's priority is greater than abstraction. So first we will perform X, Y, and YW, then we will abstract, right?
Yes, that you have done. That's not a problem. That's not a
Then
problem.
Y will also be a bound variable. If
No,
we
no, why
perform X, Y, and YW first, then abstract on Y and X.
no. Just think of this. This is the body, function body, right? And this is some application that is happening, right? This is some YW application that is going to happen. So what you are doing here, this is not application of Y onto W. This is, you are passing Y and W onto this abstraction, right? So that is what you have tried to write here. So xy
But
is
in the,
free
like
in,
if we take xy bracket xy as e1 and bracket yw as e2, so while like in the next slide it was said that first we will perform abstractions, like first we will perform application, then we will perform abstractions.
yes.
So in that case, like first we will perform like the application of xy and yw, then we will perform abstractions, right?
Okay. In notationally, okay. I'll change that notation then. Okay, I'll change that notation. I'll put a parenthesis here. That will resolve. So if I put a parenthesis here, then that resolves it. What I wanted to mean is this is an abstraction. Lambda x, lambda y, xy is the abstraction. So think of a parenthesis here. Think of a parenthesis here. So this is an abstraction that is being applied onto yw. Now in this abstraction, x and y are bound. But in this part, y is not bound because there is no lambda y on that. So if you just think of a parenthesis here, then it will. I understand. Possibly I should have done that. This is creating the confusion of what is being. Is that okay?
Yes, sir.
Okay. So let me again go back and see if there are other questions. Thank you very much, Akshat. Thanks for pointing out. Any other question? Anybody?
Can you please explain the twice example for like the function of f of x once more?
Uh, that yes, this one. This one you're saying, right? Akshay?
So it's Tanmay, and yeah, I'm saying this.
Okay, okay. It takes a time to get updated, the view. So you see what we are saying here is I'm defining an lambda expression. And what is that lambda expression? This is a there are two variables f and x. And this is the body, right? So what is that body? The first is fx. So what is this? This is an application, right? So f is applied onto x, right? So what will happen? So in simple terms, what you see is I have called f on x with x as a parameter. So I'll get a result out of this, which is the fx lambda expression. And then I'm applying f onto that result. So I'm applying a lambda expression f onto this lambda expression, right? So I'll get a second application of f on x. So that is the reason I'm just calling it twice. You can call it anything else, but I'm just calling it twice.
How in
So
the like example evaluation 7?
yes, this is f. This whole thing is f, and this is x. So it is an application where you take this whole lambda expression. You have two parameters, so you need two values here. So this is the value of f, which is lambda n dot add n1. This is the whole thing, and 5 is the second parameter, which is x. So if you think of this expression, what will happen? X is 5 and f is this lambda expression. So you are applying this lambda expression on 5. So which means that you will take n as 5 and evaluate this body, replace n here. So this fx part becomes add 5 1, which is 6. So now what you have is f6. What is f? F is this lambda n dot add n1. Now instead of 5 here, think of 6. So what will it do? It will replace n by 6. So you have add 6 1. That the result 7.
Okay,
Does
sir.
it clarify?
Yes, sir.
I think somewhere I have in longhand also I have worked out. If not, then I'll work it out again. Is there any other question from anybody? Okay, then let me continue. So now what I'll do, I will give you a set of examples and show you very interesting things like how you can build up Boolean algebra. You all are familiar with Boolean algebra, right? Of and or not, the basic fundamentals of digital circuits and all that. How can you build up even Boolean algebra or normal integer arithmetic using lambda expression? So we'll, and then finally we will look at how can you define recursion in lambda expression, because as you know, expert programmers, all of you are, I'm sure you are very prone to using recursion in expressing your thoughts, because that's a easiest way to do things in algorithms. So this is a build up towards that. So certain functions that you need very often are given as examples. So the first function that I introduce is identity function. So it is lambda x dot x. This lambda expression is called an identity function. Again, I'm reminding that ID, I'm just giving it a name. That's not a part of the lambda expression. Lambda expression is just whatever is on the right hand side, but I'm just giving it a name. So what will happen? What is IDE? If I apply it on some lambda expression E, what will happen? Is lambda x dot x applied onto E. So x will be replaced by E, so you'll get E. So here, with this lambda expression, whatever it applies on, you will get back that. So this is called an identity function. So it has a type for from A to A, and A could be any type. In fact, the functions which has this kind of characteristics that it can work on multiple types are called polymorphic function. I mean, if it rings a bell, it is the polymorphism in C++ templates you are referring to. It will get related finally there. So it lambda x dot x acts as an identity function. Okay? So this is simple. Second is a successor function, which we have already seen. Add is taken to be a predefined constant. Numerals are also taken to be predefined constant. So lambda n dot add n1 is denotes a successor function. So we'll give it a name, say SUCC, suc, which is what it does. So it gives you the successor, quite obviously. This is interesting. This is called a constant function. So if you, it is lambda x dot lambda y dot x, and if you call it a constant function identifier k, you apply it on 0, you'll get lambda x dot lambda y dot x applied on 0. So in the order, it is 0 replaces x. So you get x becomes 0. So you get lambda y dot 0. Now in this expression 0, there is no instance of y. So no matter on whatever value you apply it on, you will always get 0. So the result is 0. You do that for k, apply k onto 1, it gives you 1. Apply it on any numeral, it will give you that numeral. So that's the reason this is called a constant function. And we will again often use this, need to use this function. Okay. This is the very, very important function, which is called apply. So if you write, you have already seen this in twice. So lambda f dot lambda x fx, then what you are doing, you are applying f onto x. So if you give a function, what will apply do? Apply will take two parameters. One is a function a to b, and one is a parameter a, and then it will apply the function f onto x, that is replace the body of f with the value of x. Naturally you'll get a value in b. So apply itself is a function which takes a function and applies it onto a value. So you're saying that invocation, the process of function calling, the process of invocation itself is a function. Right? We do not think about it in that way, because all that we say, if we have to call a function, then well, I know what is the starting address of the function, so I will just copy the actual parameters onto the formal parameters and jump